Give you a day to kind of, catch your breath, get back in the swing of things here. There's a couple problems on the assignments that I want to just very briefly talk about, and then I'll let you work and get some questions answered. And tomorrow we'll do some new stuff. Okay, so first thing, I added the Desmos graphing calculator for the first time to an assignment, and we're going to start to use this stuff a little bit. So let me open that up. And then when you get down to these problems like evaluating functions, let's pick something like this. Actually, that one's not going to do any good on. Okay, something like that, where we're evaluating a function at a number. Okay, it might even be better. I'm going to do the second assignment. Something like that. Okay, where you get a really ugly function. So look what this is telling us here. It's kind of ugly. Okay, so something like this, where this is the way math really looks in real life a lot of times. So this is a polynomial model here that's telling us the number of cell phones sold in a city as a function of the year, right, is given to us here, where X represents the number of years after the year 2005. So for example, in 2005, what would the year, what would X be? 2005. No, 0. Right. So that's the start of our measuring of the time periods in 2005. So in 2011, it would be X would be 6. Okay. So we want to know here. We want it round to the nearest phone. We want to predict the number of phones that will be sold in the year 2017. So a lot of times we want to do things like this. We want to use a model, sometimes even repetitively, or we want to be using the same model over and over again. I used to do a lot of this with the TI-84s, but more and more I just use Desmos now. And I'll eventually show you how to do this on the TI-84s as well. But for now, let's start with Desmos. Desmos is, you can pull it up on your phones. It's something that's immediately available. Any computer, it's available. It's what you'll use on SBAC. I think it's likely that in the future it might even be something that's used on other standardized tests. So it's worth getting familiar with. So here's one way you can do this. I think I've showed this to you once, but we've never really used it, so I'm going to show it to you again. So one thing we could do is we can just build the function in Desmos. It's a lot easier to enter stuff too than on a calculator. Okay, so what's the advantage of using something like I want to pick the year 2017? So what value of X would that be? 12. Okay. So do you see the advantage then if I just did n of 12? It gives me the value right there. And now, so if I wanted to do something like pick other values, it's really easy to do, right? I can just go back and overwrite the value of the input variable, right? The input value I'm putting into the function, and it's really simple to get repetitive values in. So otherwise, it's just difficult. I mean, if you're trying to do this on a calculator, it's a lot of input, right? It's easy to make a mistake. This way, I think it really is more accurate and easier to do. Okay, so take advantage of Desmos. It's available. I embedded it in the first assignment. On the second assignment, it's not actually. Oops, darn it. The second assignment, I just put it as a link before the assignment. So there it is, right? So if you click on that, you can open up the Desmos graphing utility. You might bookmark it too. Okay. All right, so other issues. What about stuff like that? What could I do with that? So what's this asking me to do? What, v is a function of x. Is x the radius?
Yeah.
Oh. What's the radius? 1/2 x. Yeah, right? So if I wanted to come up with a function, volume as a function of x, what would I do? We know the volume formula typically is given to us in terms of radius, right? But in this case, we're not given radius per se. I mean, we are. We're told radius is 1/2 x, right? How are we gonna take this volume function? Because right here, this really could be written as v of r. Right? We've got r is the input variable, right, that we're using to calculate volume. But what are we going to do with that r? Substitute a 1/2 x. Right? We're told right here that r equals 1/2 x, or just x over 2. So there's my substitution equation. Remember talking about this? I mean, it's been a long time ago, right? Been over a week ago, I guess. But this is what we talked about this a little bit before the break. So one thing that I think is a good idea when you're doing stuff like this, I always, because we do this a lot in calculus, for example, I always tell my students that when they figure out what the substitution equation is, put a box around that, because it's easy to find and typically you'll come back to it. So a lot of times we'll do things like, okay, if this is how the radius is defined, and we're going to plug this in and get some function v of x, well, a lot of times we'll do something with that. We'll solve an equation, and we'll want to know, okay, so eventually, what is the radius at the solution of the equation? Well, there it is. There's r written as a function of x. So if I were to solve an equation for x, I could just go plug it back in, right? We're not doing that right now. That's kind of maybe the next step. But I would just end up, wouldn't I, then, with something like this? V of x is just going to be 4/3 times pi times r, which is x over 2 cubed. And then I would just go through a simplification process then, right? I would just simplify this by simplifying this quotient, right? If I have a quotient to a power, I just distribute the power to both parts, and I can multiply straight across and reduce fractions, etc. Right? That's kind of where the algebra comes in. Okay? That make sense? Yes. Let's look at one more of those. What about... So stuff like this. And there's going to be some variability in these, but now we've got, we want to come up with the area of a right isosceles triangle as a function of leg length x. Well, that one's pretty straightforward. You might have to draw a picture. Right, what's a right isosceles triangle look like? Okay, and the legs are the same length, and we're saying the leg length is x. So there's your triangle. No big deal. You can come up with the area of that. If you want to move forward with that, you pick a little harder. Okay, something like this. If we want to represent the area of a square as a function of the diagonal d, that's not as obvious, right? That's something where we're going to have to do this a little differently. If I draw a square, let's just call the side length x, right? I want to come up with area as a function of d. Where am I probably going to start? That's not something we automatically know. What do we know? Yes, Caleb?
Find the area of the right triangle.
That's an approach you could take, sure. We probably don't need to do that. I mean, we know the area of a square, don't we? What is the area of a square? X squared. So we know the area as a function of x, right? We know that a of x is x squared. We want it as a function of d, though. So what's my strategy going to be? And I want you to think about this. You got to be kind of forward-thinking here. This is the way math becomes as you get further along. If I want to get from here to there, what am I going to do? Without being specific. You just kind of know your strategy's already mapped out. Yeah, I just need a substitution equation, right? I need x as a function of d, and if I can do that, then I can make my substitution. Think what we're trying to do. We're trying to get away from x's towards d's. So we want to be able to replace all of the x's completely with some expression involving d's, and then plug them in and simplify. So what's that going to be? Here's the diagonal. And there's x. Well, I'll let you think about that. But you can find a relationship there, can't you? Right? Okay. A relationship where I could say d equals some function of x, right? Other way around, some function of d, right? That make sense? Okay, last thing I want to show you. So review that, and then okay, something like this. So what are my approaches to doing a problem like this? So we're given a function f of x equals some quadratic expression, ax squared plus bx plus c. A, b, and c are fractional this time. And we want to solve for f of x equals -5. So what's that mean? Say it again.
Don't substitute -5.
No. That would be different. That would be a question that would say evaluate the function at x equals -5. This is different.
Set the equation.
Okay. Yeah, the -5 is f of x, right? So the -5 is what we're substituting for f of x, right? If we do that, if we set f of x equal to -5, we just come up with the equation -1/4 x squared minus 5/2 x minus 41/4 equals -5. There's an equation we can deal with, right? Okay. It's, you're going to have a strategy. Probably what's the first thing we want to do with something like this?
Get rid of those fractions.
Yeah, we want to clear the fractions. So we're going to multiply each side through by what? 4. Okay. Maybe even, instead of 4, maybe even what? -4. Good. How come? We want a to be positive, right? We want to set this up in standard form where it's equal to 0 and a is positive. So we multiply both sides by -4, clear the fractions, push the constant back to the left and set it equal to 0. And then you guys are great at this, right? Then it's just a matter of solving a quadratic equation, okay? There is a little trick. Now, you're not going to have access to this on the test necessarily, but I want you just to be thinking ahead a little bit because we're going to be going here with this pretty soon. Could we use Desmos here in a way that would be useful? How could we maybe use Desmos to solve this equation without doing algebra? And you got 3 of these to do. I mean, to try it once just to get a little practice. But I want you to do the algebra. You still need more algebra practice. But how could I use Desmos in this situation? So here's Desmos. Instead of n of x, let's call it f of x. I'm going to enter the function just like before. Oh, I do. You're right. So there's my function, right? There it is. So what about this? How am I going to use that graph to solve this equation right down here? The function equals -5. Oh, okay. I could graph another line there. I could graph the line y equals -5. And what do you know? I've got intersections in those two places. So what are the solutions then to this equation? Everybody see? -7 and -3. We want the x values, right? We want the x values where the function is equal to -5. So that would be where the red graph, which represents f of x, crosses the green graph, which represents -5. That's a general strategy, right? We can say that if we ever want to solve an equation graphically, I can graph the left side of the equation as one function, the right side as another, and look for intersections. Okay, that's a pretty quick and easy way to do it if you have a graphing utility available. Okay, what if this had said instead of -5, what if it had said +5? Oops. What's wrong there? Doesn't have any. Doesn't have any. Does it not have any solutions? It does have solutions. It has to, right? I mean, every quadratic equation is going to have solutions. I can just plug it in the quadratic formula, and I'm guaranteed to get solutions. But if I set this equal to +5 instead of -5, what can you probably guess about the nature of the solutions? They're imaginary. Yeah, right. They're complex solutions with imaginary parts, right? And so, yeah, we don't get any real solutions. So real solutions would correspond to intersections. Non-real solutions don't correspond to actual intersections of the graph. Okay? We'll talk much more about that. I just want to give you just a little look ahead of kind of some places we're going with this. All right, you can have the rest of the period to work on stuff, get questions answered. You got 2 assignments up. Tomorrow we'll look at some new material.